In 1929, Edwin Hubble placed a small collection of galaxies on a graph. Distance ran along one axis. Radial velocity ran along the other. The points were scattered and the distances were uncertain, yet a pattern emerged: more distant galaxies tended to recede faster. The graph became one of the central pieces of evidence that the universe is not static. Space itself is expanding. That famous result was not the work of one man or one night. It depended on several discoveries that had to be joined together. Spectroscopy supplied velocities. Variable stars supplied distances. General relativity supplied a framework in which the universe could change with time. Hubble's paper made the observational relation difficult to ignore. Begin with light. When a gas emits or absorbs light, it produces spectral lines at characteristic wavelengths. Hydrogen, calcium, and other elements leave recognizable patterns. If the source moves away, those patterns shift towards longer, redder wavelengths. We define redshift, Z, as the observed wavelength minus the emitted wavelength, divided by the emitted wavelength. At speeds much smaller than the speed of light, the radial velocity is approximately c times z. This is the ordinary Doppler interpretation used for nearby galaxies. At large cosmological distances, however, redshift is not adequately described as galaxies simply flying through a fixed arena. The expansion of the universe stretches the wavelength of light while the light travels through evolving spacetime. The early velocity measurements were pioneered by Slipher at Lowell Observatory. Beginning in the 1910s, he measured the spectra of what were then called spiral nebulae and found that most were redshifted. Hubble did not personally obtain most of the velocities used in his 1929 table. He drew primarily on published radial velocities, especially Slipher's work, and applied a correction for the sun's motion. Velocity was only half the problem. Astronomers also needed distances far beyond the Milky Way. Henrietta Swan Leavitt had discovered a relation between the pulsation period and luminosity of Cepheid variable stars. Once calibrated, a Cepheid's period gives its intrinsic luminosity. Compare that with how faint the star appears, and the inverse square law gives its distance. Hubble used Cepheids to establish that objects such as the Andromeda Nebula were separate stellar systems beyond the Milky Way. For his 1929 velocity distance paper, however, only some distances rested directly on identified stars. Others used the apparent brightness of the brightest stars or an assumed average luminosity for galaxies. The distance scale was therefore substantially underestimated. Hubble's original sample contained 24 individual nebulae, plus group data. When he plotted velocity against distance, he obtained an approximately linear trend. In modern notation, recession velocity equals the Hubble parameter times distance, v equals h0d for the nearby universe. His numerical value was roughly 500 km per second per megaparsec, far larger than modern estimates. The main reason was not that the universe radically changed its local expansion rate within a century. The galaxies were farther away than the distance calibration then indicated. Correcting the distance ladder lowered the inferred value. There is another crucial historical qualification. In 1927, Georges Lemaître had already derived expanding universe solutions from Einstein's equations and combined available distances and velocities to estimate a proportional relation. Alexander Friedmann had found dynamical solutions earlier still. Hubble's 1929 paper supplied an influential observational demonstration, but the interpretation of cosmic expansion emerged from theory and observation together. The relation is now often called the Hubble-Lemaître law. What does the law mean? Imagine points drawn on an expanding rubber sheet. As the sheet stretches uniformly, every pair of sufficiently separated points moves farther apart. A point on the sheet sees distant points recede faster because more expanding space lies between them. There is no privileged central point on the two-dimensional sheet itself. The analogy is useful but limited. The universe is not known to be a sheet expanding into an external room. The expansion is a change in the scale that relates large, unbound distances within space. Gravitationally bound systems do not simply swell with the Hubble flow. Atoms, people, planets, solar systems, and most galaxies are held together by forces far stronger than the present cosmic expansion across their size. The wavelength picture makes the same idea visible. Mark successive crests on a light wave traveling through expanding space. As the cosmic scale factor grows, the separation between crests grows with it. The observed wavelength is the emitted wavelength multiplied by the ratio of the scale factor now to the scale factor when the light was emitted. Cosmological redshift therefore records the change in the universe during the light's journey. For nearby galaxies, where redshifts are small and cosmic evolution during the journey is modest, the linear Hubble-Lemaître law is an excellent approximation. At great distances, one must use the full relation supplied by a cosmological model. Recession rates defined from changing proper distance can even exceed c without any galaxy locally outrunning a beam of light. Special relativity limits local motion through spacetime. It does not require a global distance between faraway comoving galaxies to change more slowly than c. The expansion also gives a rough cosmic timescale. If the expansion rate had always remained constant, the inverse of h0 would estimate the time required for the present separations to develop. The real expansion rate changes as matter, radiation, and dark energy influence cosmic dynamics, so the inverse Hubble parameter is a scale, not by itself an exact age calculation. Hubble's graph did not prove every feature of modern cosmology. The original data were sparse, the scatter was large, and the calibration was wrong. Its importance lies in the correlation. Distance and recession were connected in the way an expanding relativistic universe led physicists to expect. Later observations extended the relation enormously and refined the distance scale. There is an Aristotelian lesson in how the discovery was made. Measurement supplied particular facts, specific spectra, periods, brightnesses, and distances. Mathematics disclosed a common relation among them. Physical theory then identified the kind of change being measured. None of those levels replaces the others. Together they convert a cloud of observations into intelligible knowledge. So the expanding universe story is more accurate and more interesting than a lone astronomer noticing red lines. Slipher helped supply the velocities. Leavitt's variables made the distance ladder possible. Friedmann and Lemaître showed that Einstein's geometry could expand. Hubble assembled distance and velocity into a graph whose upward trend transformed the debate. The equation is simple: nearby recession velocity is proportional to distance. The implication is immense. Galaxies are not merely scattered through an eternal static container. On the largest scales, the distances between unbound galaxies evolve. A few dozen points on a page revealed a universe in motion.